Finding a specified term of a geometric sequence given the common ratio and first term. Before we get started here, I do want to remind you that you've studied the things of exponential decay. For instance, if I give you a short graph here, here's f of x, there's the f of x axis, and here's the x axis. And you may have studied the function f of x equals 1/2 raised to the x power. And that's obviously an exponential decay. It'll go something like this, approaches the x-axis. Well, in some ways, sequences just represents certain ordered pairs. If you just look at n equals 1 and n equals 2 and n equals 3, then we're going to see a sequence of dots here that are actually approaching 0, right? The y value would be 0. It's approaching the y value to be 0. If you go to 4, the values are getting lower and lower and lower. And of course, if you calculate that, it will indicate that as well. If you take f of 4, you get 1/2 raised to the 4th power, which is 1/16. So certain patterns, these little blue dots, sometimes they run in a very, very nice pattern, and they're worth investigating. Sequences is actually the introduction of something called series, and you're going to see series pretty soon as well. So let me try to give you an example of those blue dots, but instead of seeing it as a decreasing exponential decay function, why don't we draw some geometry? After all, we are looking at geometric sequences. So let me erase the board here. And I'm going to show you the pattern of those blue dots in a very, very different way now. I'm going to first start off with a 1x1 square. And it's 1 unit by 1 unit. 1 by 1. And if it doesn't look square, pretend it is a square. Looks like I drew it too long. I draw it right here. And let me erase these extra blue dots. So there is a 1 by 1 square. Now what I'm going to do is cut that in half. And now you're going to see the base of 1/2. But what happens when you cut 1/2 again? Let's cut 1/2 again. This time we go this way. And now you get 1/4. And what happens if you cut 1/4 in half? Well, then you get 1/8. And what if you multiply 1/8 by 1/2? Then you get 1/16. What if you take that 1/16 and multiply it by 1/2 again, or cut it in half? You get 1/32. And what happens if you cut 1/32 in half again? Then you get 1/64. So are you seeing a pattern here? Obviously, this is counting numbers according to the base of 1/2. It's also a ratio too. You could see the ratio of 1/2 as well. Now here's the question. I'm going to ask you this. So here's a sequence of numbers. 1/2, 1/4, 1/8, 1/16, 1/32. Now I'm just simply going to put a plus sign in between here. So they were a sequence of numbers and with a very, very specific pattern. Now obviously if we stop at 5 terms, you could easily find its sum. Now I'm going to ask you to not stop at 5 terms. I want you to put 3 dots at the end and never stop adding these terms. What would happen? Keep adding those terms. The next one would be 1/64. The next one would be 1/128. Keep doing that and see what happens. In other words, ask yourself this. Does the sum exist? And I'm going to tell you something. The answer is on this page. I'll let you think about it. I'm going to go back to geometric sequences. Let me clean up the board here. Let's look at example A. Find the ninth term of the geometric sequence whose common ratio is 1/2 and whose first term is 8. The first thing you want to do is actually write the definition of a geometric sequence. A sub n is equal to a sub 1 times the common ratio raised to the n minus 1 power for n equals 1, 2, 3, dot, dot, dot. Now remember that is the domain of this function. Okay, it would just graph the outputs of dots, or the output that consists of ordered pairs, right? It's a discontinuous function. Okay, well, we already know the first term. We know that the first term, a1, is 8. We also know that r is equal to 1/2. And we want to find the ninth term. So first of all, I'm going to write the formula, or the sequence. Here's the function. A sub n is equal to 8 times 1/2 raised to the n minus 1. That's not my final answer, but this is necessary work. Now we're going to find a sub 9. We want the expression a sub 9. A sub 9 would then be what? 8 times 1/2 to the 9 minus 1, which is 8. And of course, you could take your calculator there and get this final expression. An exact answer would be 8 over 2 to the 8th power. 2 to the 8th power is pretty big. 8 over 256, which reduces to 1 over 32. I'm going to put a period here. Therefore, a to the ninth is equal to 1 over 32. I'm going to circle this as well. You really should write that. Write your function, or write the geometric sequence. Find a 10th term. Oh, I should circle all the work in between. Might as well just circle everything. Let's do example B. If you want to, you could pause the video and try it yourself, and then unpause it to check your answer. Find the 10th term of the geometric sequence whose common ratio is 3/2 and whose first term is 4. Once again, we can write the definition. B sub n is equal to b sub 1. How about that? B sub 1 common ratio times the common ratio raised to the n minus 1 power. And we know r is equal to 3/2, and the first term is 4. B sub 1 is 4. So let's write our sequence, our geometric sequence. 4 base is 3/2, or the common ratio is 3/2, and then raise it to the n minus 1 power. I'm going to circle this, even though it's not the final answer. We want to find b sub 10. B sub 10 is an expression. We're just going to manipulate this expression here and raise to the 9th power. Let's see what this gets. This is 4, which is 2 squared. So we have 3 to the 9th over 2 to the 7th. And let's see what that is. And since there are no common factors, there are no common factors. 2 and 3 are prime numbers, so that will be the final answer. Therefore, b sub 10, your final expression is b sub 10, which is 19683 over 128. Circle our answer in our work, and we're done. For a given geometric sequence, the third term, a sub 3, is equal to 11/16, and the eighth term, a sub 8, is equal to 22. Find the value of the 12th term, a sub 12. If applicable, write your answer as a fraction. The first thing you want to do is write the formula for a geometric sequence. That is, a sub n is equal to the first term times the base, or the common ratio, r, raised to the n minus 1 power. We don't have the common ratio. We don't even have the first term. We do have a sub 3. A sub 3 is the third term, which is equal to 11/16. A sub 8 is equal to 22. So why don't we use these input and output values to figure things out? So I'm going to highlight this. This is 11/16. And that occurs when n is equal to 3. So we're going to put 11/16 here, which is the output. And we have what? We have a sub 1 times r. And then we know what n is. N is 3 minus 1. N is 3. So 3 minus 1 is 2. So we get this equation called 11/16 is equal to a times r squared. We're going to use the other equation as well. Let's use the fact that a sub 8 yields 22. So our output value is 22. Our output value is 22. And when does this occur? This occurs when a sub 1, which we don't know, is multiplied to r, which we don't know. But we do know that n in this specific case is 8. So what's 8 minus 1? I'm sure you guys can do that. That's 7. So we get this new equation here. We get 22 is now equal to a sub 1 times r to the 7th power. It would be nice to be able to find the common ratio. There's a couple things we know. We know that a sub 1 is not 0. We also know that r, the common ratio, is not 0. If either one of these are zeros, we won't be talking about a geometric sequence. So we know that by definition, a sub 1 is not 0. The common ratio is not 0. Let's take this first equation over here, and I'm going to solve for a sub 1. So that is going to be 11/16 times r squared. I'm going to take this and substitute it over here. And let's see what we get. 22 is now equal to a sub 1, which is 11/16 times r squared. And r to the 7th power. Now we have r to the 5th power. We got 22 times 16 divided by 11, which is equal to r to the 5th power. That's 2 times 16, which is 32, which is equal to r to the 5th power. I'm going to take the 5th root of both sides, not a problem. 5th root is a 1-to-1 function, so we get r is equal to 2. So we get the common ratio to be 2. Now we need a sub 1. I'm going to go back to, let's say, this equation here. Let's use that equation to get a sub 1. So going back to the triple star equation, I'm going to solve for a sub 1, which is 11/16 times 4, which is 64. And there is a sub 1. Awesome. We need to find the value of the 12th term. Well, we're not quite there yet. I'm going to write the new sequence, geometric sequence, a sub n is now equal to 11/64 times r. R is 2 raised to the n minus 1. And that is really, really key. Even though this is not the final answer, we need this in order to find the 12th term. Remember, a sequence is a function. So our output value is what? The expression that we're looking for is a sub 12. Let's find a sub 12, which is just 11/64 times base 2 raised to the 11th power. And of course, you could put that into your calculator and figure that out. 22528 over 64. This is reducible by 4, so let's write the expression again. 5632 over 16. This is once again reducible by 4. So let's reduce it again. Now you're probably wondering, how come I know it's reducible by 4? If the last two digits is divisible by 4, then the entire number is divisible by 4. Just like this is divisible by 4 again. So this is going to be a really nice number. This is now 352. 352. So the 12th term, therefore, a sub 12 is equal to 352. There's your final expression. I'm going to circle, well, you could just circle the whole entire page. There's a lot of work involved here. I am going to circle the final answer, but make sure you can show your work. The sum of an infinite geometric series. Compute each sum below. Give exact values, not decimal approximations. Notice there are three series here. And a series is what? Is actually a sequence where you add those sequence terms an infinite number of times. So here is the concept of infinity. Those three dots here says that we will add things forever and forever and forever and forever. This is sort of strange. Why would we add things forever, forever, and forever, and forever? Well, sometimes we run into those situations where we need to make predictions off of reiterations. Same thing here. Here's the concept of infinity. You're going to add these terms over and over and over again. And there's only two things that could happen. You either have a sum that is finite, and finite in this case means tangible, reachable, concrete. It is a real number, and that's what we mean by finite. Or you get something that's not finite. In other words, you would say the sum will not exist. It's not reachable. You can add things forever and forever and forever, and you won't get to something that is tangible. Now, I'm going to do this a little bit differently. I'm going to give you what I call a calculus technique on how to find the sum of a geometric series. I'm actually going to take a very, very simple series. I'm going to take this geometric series where you just have a common ratio raised to the k power, but we're going to start k at 0 and then run this to the concept of infinity. Notice this really just says r to the 0 plus r to the first power plus r squared plus dot dot dot. And of course, if you simplify that, the first term is always going to be 1, and then plus r squared plus 3 dots. Now this actually converges to 1 over 1 minus r if the absolute value of r is less than 1. Now I'm going to write this much cleaner, and typically in mathematics we could write things in an if-then statement. So if the absolute value of r is less than 1, big comma, big comma, big comma is right there. Then we make this conclusion. Then the geometric series r to the k, starting at k equals 0 to infinity, is simply going to be 1 over 1 minus r. And that is a beautiful sum and rather simple formula. We're going to use this formula to figure out the sums in A, B, C, and D. Let's start with A. Example A. So I'm just going to start off by copying the problem again. And I can see that there is a common factor. And that common factor is 2 times negative 5. And let's see what's left. What is left? Well, we have a 1 plus a what here? A negative 5, right? If you multiply, if you distribute, you're going to see that you have 1 plus negative 5 plus another what? A negative 5 squared. So we're just simply taking your factoring skills and seeing that there is a nice geometric series here. So this is now equal to what? This is now equal to negative 10 times this geometric series, which is negative 5, negative 5 is the common ratio, and I'm going to use k. There it is. And I'm going to put a period there. Since the absolute value of negative 5 is actually equal to 5, which is greater than 1, we could make this conclusion. The sum does not exist. And we're done. So in this case, we couldn't find the sum, but you did have to show the work and evidence to see that the sum doesn't exist. So I'm going to circle this. And then this is your final answer. Final answer is pretty meaningless unless you show your work. So that's why I just circled the whole thing. I'm going to need more space for example B. So I'm going to go ahead and erase the board. If you need to, remember to pause the video. Example B is very, very similar. Can you see a greatest common factor from all those infinite terms? I'm going to first recopy the problem. So 4 plus 4 times negative 3/7 plus 4 times negative 3/7 squared plus 3 dots. Don't forget those 3 dots. That means you're running this to the concept of infinity. We're going to add this an infinite amount of times. There is a greatest common factor, and that is 4. Every term has a 4. Let's factor out a 4, and let's see what we have left. We have a 1 plus a negative 3/7 plus a negative 3/7 squared, and we indeed have a geometric series here. This is now equal to 4 times the summation, k equals 0 to infinity of the common ratio of negative 3/7 raised to the kth power. We do know that this converges, so why don't we just keep writing? We're going to say 4 times 1 over 1 minus negative 3/7. We could certainly simplify this. I'm going to multiply by 7 over 7. Let's see what we get. We get 4 times 7 in the numerator, all over 7 plus 3. Gorgeous. And 7 plus 3 is just 10. We could reduce factors. So 2 over 5 times 7. So 14 over 5. And who would have thought adding all those infinite numbers will simply get you 14 over 5. So there's the final expression for part B. Notice in part B you're not solving for anything. You're simply manipulating this expression right here. You started with this expression and you ended with this final expression. I'm going to go ahead and circle all the work as well. Moving on to part C. Part C says there's a series here where the sequence terms are 5 times the common ratio of 1/2 raised to the kth power. But we start with the index of k equals 1 and we run this to the concept of infinity. Let's copy the problem again. And what do all these terms have in common? Well, all these terms have a 5 in common. So let's factor out a 5. And I don't really want to start with k equals 1 here. I would love to start where? I would love to start with k equals 0. If we're going to get this to k equals 0, we know it converges to that. 1 over 1 minus r. So, how can we get this to start at k equals 0? So we're going to re-index everything here. I'm going to show this off to the side here. We're going to replace k with k minus 1. Yeah, that's going to do it. So if you replace k with k minus 1, what happens to this equation here? So you replace k with k minus 1, then you get k minus 1 is now equal to 1. Oh. Excuse me. Don't replace k with k minus 1. I meant to say replace k with k plus 1. Then this equation over here, if you replace k with k plus 1, then we get k plus 1 here is equal to 1. So let's put a k plus 1 there is equal to 1. And if you solve for k, we now start at k equals 0. All right, we got it. 5 summation. Now we have k equals 0. Run that to infinity. Then we have 1/2. And we replace k with k plus 1. So this is k plus 1. These are in fact the same geometric series, starting with a different index. Now, what do all these terms have in common? These all have a 1/2 in common. You could easily see that by mastering your rules of exponents. And now you can see there's a common term of 1/2. I'm going to take this 1/2 right here. Every single term actually has this 1/2. So let's factor that out. We have equals 5 over 2 times the series and that is gorgeous because we could actually find its sum. This is multiplied now to 1 over 1 minus 1/2, which is just 1/2, by the way. This is going to be 5. Who would have thought the final expression would be 5 after adding all those numbers together? Let's go ahead and circle the final answer. But once again, show your work. Without your work, your answer is pretty much meaningless. Moving on to example D. Oh, did I say example D? Yes, I did say example D. This one got mislabeled. We actually did C. So why don't you get a head start on example D while I just erase the board here. Example D, the series starting with j equals 1 to infinity times 3 with the common ratio of -4/7 raised to the jth power. Now, what do all these terms have in common? All these terms have in common is a 3 times -4/7. Yeah. And what's the first term now? I might be going too fast. So why don't I show you what I'm doing here? Let's write out the first few terms. This is 3 times -4/7 plus 3 times -4/7 squared plus 3 times -4/7 to the third power. And this never stops. I'm going to write the next expression, which is the greatest common factor, 3 times -4/7, and let's see what's left. What's left is a 1 plus a -4/7 plus a -4/7 squared, and so on and so forth. This is a nice and easier approach. Now we have what? -12/7 as the greatest common factor. Multiply it by the series. I'm going to use k equals 0 to infinity. The common ratio is -4/7 raised to the k. We know this sum is going to exist because the absolute value of 4/7 is 4/7, which is less than 1. So knowing that, we could just keep writing to find the sum. And I'm sure you could take it from here. I'm going to multiply top and bottom here by 7, another fancy name for 1. And let's see here. We get negative 12 sevenths times it by 7 here over what? 7 plus 4, which is 11. Yeah. This is a really nice number. This is just negative 12 over 11. That is the final expression. Make sure you show your work. Be neat, be orderly, and be amazed. You add up a bunch of numbers, well, not a bunch of numbers, but an infinite number of numbers, and it could actually sum up to something very finite or concrete or tangible. Not always the case, but this is still truly amazing.